Bom, boa tarde a todos. Vamos iniciar esse colóquio especial do CBPF, aproveitando a vinda de vários professores aqui para a 19ª Brazilian School of Cosmology and Gravitation. Então, hoje vamos ter aqui o prata da casa, né? Gustavo Brito, o Gustavo Pazini de Brito. Ele fez doutorado aqui com o Elael e também com o Antônio Pereira, que está aí, né? Não está vendo ele? E eu, é um pesquisador dedicado à gravitação quântica, as várias ideias para quantizar a gravitação, em especial o método de segurança sintótica, como é que fala em inglês? Segurança sintótica safety, segurança sintótica, né? E então um pesquisador que tem se destacado muito nessas pesquisas. E ele vai falar de uma maneira mais coloquial, né, sobre esse grande empreendimento da física teórica, que já de longa data, que é tentar unificar a gravitação com a mecânica quântica. A gravitação, em geral, é usada para descrever a física em larga escala, as galáxias, o universo. A mecânica quântica é muito pequena, por isso o título do seminário, que é Quantum Gravity Towards the Unification of the Microcosmos with the Macrocosmos, ou, né, unificação do microcosmo e macrocosmo. Né? Então, Gustavo, prazer tê-lo aqui. A palavra é sua.
Obrigado. Vou em inglês ou português?
Alguém não fala português? Someone doesn't speak Portuguese? Ah, ok. Ok. Inglês.
So then I go in English. Okay. Thanks. Well, let me start by thanking Nelson and the other organizers of this event. It's a great pleasure to be here to give this colloquium. I'm always happy about coming back to CBPF, but I mean, especially in this occasion, I'm really happy about this. So I made a slightly modification on the title. So the original title on the advertisement was the unification of the microcosm with the macrocosm. And I added this words here because, I mean, to be fair, we still don't know how to unify those things. So what we are trying to do is to get there. So that's why I added this slight modification here. So let me start with my favorite question to start presentations. What are the fundamental building blocks of our universe? That's essentially the questions that we try to answer with physics in general, and in particular, the question that's led us to quantum gravity. So to explain what I mean with this question is, let me start with a simple version of our universe. So instead of starting with our universe, let's start with a universe of the Legoland. I lived in Denmark for 3 years, and they are very proud about Lego in there because Lego is originally from there. So in honor of this years in Denmark, I'm going to use this as part of my presentation. So the universe is a very complicated thing, but if the universe was made of Legos, we could say that the building blocks of our universe are just these Lego bricks. That's essentially what we want to do in physics and in quantum gravity and in physics of fundamental interactions in general. Okay? We made a lot of progress in this direction during the last century, and actually a bit longer than that. I'm going to start with some of the breakthrough ideas that brought us until the moment, so until the point that we are on understanding the fundamental building blocks of nature. So the first breakthrough idea was that the universe, that large stuff are composed of very small stuff. As a matter of fact, if I'm not mistaken, Feynman chose this idea as the idea that we should pass on if our civilization lost all of our knowledge, and the future civilization need to reconstruct what we know about nature. So this idea here that large stuff are composed of small stuff, it's a very important idea on physics. And what I mean by that is, suppose that we have two very different macroscopic objects. We can see here this brick of wood and this laptop. They are very different things. But we know that once we start to zoom in on things, we start to see similar structures. The first zoom in here, we arrive at structures that we call atoms. For a long time, that was, I mean, for some time, the idea was that this was the smallest stuff that we had in nature. But now we know that atoms are composed of even smaller stuff. So there is the nucleon and the nucleus, and there are electrons in this atom. And so far as we know, electrons is one of the fundamental building blocks that we know. But the nucleus composed by protons and neutrons, this is not fundamental. We can break this even more. So inside protons and neutrons, we have even smaller structures that we call quarks. So this scale here, 10 to the minus 18 meters, is essentially the minimal scale that we know that matter is composed. So everything that we see here in this room boils down to this kind of structure. Okay? The second breakthrough idea is that this small stuff behaves in very different ways from big stuff. And what I mean by that is that there is something that we call quantum physics or quantum mechanics. So quantum mechanics is, I mean, in quantum mechanics, the state of a given system can be a combination, a linear combination of substates. And in an interpretation based on Feynman's idea, we know that there is no single trajectories between two events. Actually, we have a superposition of trajectories, and these things, they interfere with each other. And what we can actually think about is the amplitude to go from a given state to another state. That was the original idea of quantum mechanics. Later, we realized that if we combine this with another breakthrough idea of modern physics, that space-time is just a single thing, and that we can create and annihilate matter, we arrive at something that we call quantum fields. We arrive at something that we call quantum field theory. So quantum field theory is the fundamental building block that, or quantum fields are the fundamental building blocks that unifies special relativity in this form, so physics of things moving fast, with physics of very small stuff. And with this unification based on quantum field theory, we were able to arrive at the Legos of matter. So now we know that the visible universe essentially is composed by a bunch of particles. And they particles, these parts, so we have different types of particles. So we have the leptons, we have neutrinos associated with leptons, we have quarks, we have antiparticles, and all these particles, they interact in terms of three different kinds of interactions. And the interactions, they are mediated by what we call gauge bosons. So some of them interact electromagnetically, and this is intermediated by the photon. The weak interactions is mediated by the vector gauge bosons, and the quarks in particular, things that are inside protons and neutrons, they interact by exchanging gluons. And on top of all that, there is this extra piece here that is the Higgs, which is a field responsible to generate masses to these particles, to quarks and to leptons, and also to the gauge bosons that are massive. This model of building blocks of particle physics is very successful. This was heavily tested at large colliders, such as the LHC. And one of the greatest success of this model was the discovery of the Higgs at the LHC. So this is the Higgs at the LHC, and this is the detection of the Higgs boson at the LHC. Okay? Well, this is essentially the set of building blocks of matter. But there's more than that. The other breakthrough idea is that the background of all these kind of things that I just said is also dynamic. So to explain this, let me go back to my Legoland universe. And here in the Legoland universe, okay, things are not working at the Legoland universe. It's not the battery because the pointer is working. Well, it's not moving actually. Okay, now things are dynamic again. Thanks. So in this Legoland universe, the background is just this static, this fixed stage in which we are playing with Legos. In our universe, things are more richer than that. The background is what we call space-time, and we learned that space-time is also dynamic. We learned this from Einstein, and this is what we call the general relativity theory. And I decided to, I think this was my first equation in this presentation. There will be not too many equations, but well, I have to write this one because this equation here is just so beautiful. So it has to be there. And what this equation is telling us is that in this side here, we have something corresponding to geometry of space-time. And in this side of the equation, we have the distribution of matter and energy on top of this space-time. And what this equation tells us is that matter or energy and matter is affected by curvature, and curvature of space-time is affected by distribution of matter and energy. Well, Einstein realized that this is actually more than that. This is related to gravity. So geometry is connected to what we understand about gravity or how things fall. So what Einstein realizes that Newton was calling this motion of this free fall motion due to forces, it's actually a geodesic motion in a curved space. Well, this idea has several important consequences. The first one is that Newton taught us that massive particles attract each other, and that was the origin of gravity from Newtonian perspective. But Einstein, very smugly, taught us that everything falls, even light. So even light emitted by some source is bended or falls because of some deformation on space-time. Okay? As I said, this has very important consequences. One of them is that there are these kind of weird objects in nature. We now have even pictures of them. These are black holes. These are objects that are where the gravitational field or the curvature of space-time is so large that not even light can escape from this region. What we have here is light orbiting around this kind of objects. And this was predicted several decades ago, and it was finally observed in a direct picture a few years ago, in 2019. As we heard before in the talk by José Lemos, there are also something else that we call gravitational waves. And the first time that this was observed was by the collision of two massive black holes. So essentially here is that you generate some large perturbation in space-time, and this large perturbation can propagate in the form of some wave. And this was also predicted a long time ago, but it was first detected less than 10 years ago. So during the last decade, there was several important results on the gravitational, on our understanding about gravity or the nature of space-time. Okay? The other consequence coming from Einstein's theory of relativity, or general relativity, is that the universe is expanding. And this is the basis of modern cosmology. This is the basis of our understanding on how the universe itself evolved towards, along the years, along billions of years. But that's the current understanding, the current picture, that things started from a small concentration of mass and evolved in now we understand that we observe that this evolution, we are now in a phase that we have this accelerated expansion of the universe. So this is a very large history of, and that, has been explored during this School of Cosmology and Gravitation here in Rio, and also in past versions of this school. Okay, so we have a very nice understanding of the building blocks of nature. So far, we understand that matter is composed by small stuff, and we can categorize this and describe how they talk to each other. And we understand that gravity is actually a manifestation of space-time dynamics. So we can ask the question, if we are, come on, now. We can ask the question if we are there yet. And the answer is probably no. So this is still an incomplete picture. There are other components that are not included here, so things that we call dark components of the universe. There are many other open problems related to both sides, but the one that I want to discuss here is the lack of a unified description involving space-time and matter. And the reason why we think this is important is because, well, this is the main equation of general relativity. And this side of the equation describes something classical. So this side of the equation describes the classical dynamics of space-time. And this part of the equation involves matter. And we know that matter is composed by quantum stuff. So it's still unclear how to describe these things in a unified picture. One thing we can try to do is, well, instead of including this energy momentum tensor on the right-hand side of the equation, we actually add the expectation value of the energy momentum tensor, and then we quantize matter but keep gravity or space-time as classical. It's still unclear whether this can be properly done and whether we can account for all possible back reactions and so on. The other point is that general relativity also predicts its own breakdown. So as I said before, general relativity predicts the existence of this kind of weird objects, and also the evolution. This also gives rise to this model that describes the evolution of our universe. And general relativity, unless you make further assumptions, predicts singularities at the center of black holes, but also at the origin of this evolution. Okay? So we don't know from the theory what is going on at the singularities. And this is one of the challenges that people try to address with quantum gravity. The other point is that the matter side of the equation, the matter building blocks, is also incomplete. And one way of seeing this incompletion is if you look at the running of couplings, the way that couplings evolve with energy scale. Well, in this picture here, it stops around what we call Planck scale, 10 to the 19 GeV, because we believe that something else is missing here. But if we just try to extrapolate, in particular, this G1 coupling, which is related to the hypercharged sector of Standard Model, if you extrapolate this, you get a Landau pole, which basically means that at very high energies, the theory breaks down. This is, of course, a perturbative result, so this could be just an extrapolation of perturbative methods, but we also have indications that this is true beyond perturbation theory for this kind of models, of quantum field theories, let's put it this way. Okay? So the point of view that I'm taking in this colloquium, in this presentation, is that something is missing with this description of fundamental physics, and that what is missing is the quantum nature of gravity. So the idea is that if we add the quantum nature of gravity as the missing ingredient, we can solve this kind of problems that appears both on the gravity side, in the macroscopic side, in the description of macroscopic objects such as black holes, but also in the evolution of the universe. But can also solve the problems on the matter side. For example, maybe gravity can resolve this issue with diverging couplings on the standard model. Okay? This is, I just to emphasize that this is just a point of view. It's a possible point of view. So far, to my knowledge, there is no proof that gravity must be quantized. But this is a point of view that we like to explore and see its consequences. We know that something is missing, and then the idea is what is missing. And one of the possibilities is that we need to account for gravity. We need to treat gravity as a quantum theory as well. Okay? Well, where do we expect quantum gravity to be relevant? And this is related to one of the challenges of quantum gravity. Well, one way of seeing this is by this kind of Brownstein cube. And the different corners here correspond to different regions where different phenomena are relevant. So, for example, in this corner here, where velocities are close to the light velocity, we know that we need to describe things in terms of special relativity. In this corner here, where things are small, we know that, or h bar is relevant. We know that we need to describe things in terms of quantum mechanics. If we put together these two corners, we get to quantum field theory. So adding quantum effects with special relativity effects. And if you go to a region where gravity is important, so where the Newton coupling or the Newton constant is important to describe physical phenomena, and if you go in the direction of adding quantum effects and special relativity effects, we get to what we call quantum gravity. So at this corner here, the quantum gravity corner, we can estimate some quantities. We can estimate some length scale, we can estimate some mass scale, and we can estimate some energy scale. These are the things that we call Planck length, Planck mass, and Planck energy. And in particular, let me focus here on the Planck length. So the Planck length is of order 10 to the minus 35 meters. And just recall that the size of the upper bound on the size of the electron is around 10 to the minus 18 meters. So very far away from here. If you want, you can look at things in terms of Planck energy. So Planck energy is of order 10 to the 19 GeV. And if you compare this with electroweak energy scale, this is the scale that we can use that we can access with large colliders. This is of order 10 to the 2 GeV. We see here that the ratio between the energy scale of electroweak interaction divided by Planck energy is of order 10 to the minus 17. So the conclusion from here is that we can expect that quantum gravity effects that are important around the Planck scale is highly suppressed around electroweak scale. In other words, highly suppressed in scales that we can probe with particle accelerators. Even modern particle accelerators, and as Philip was telling us in his talk earlier, if you extrapolate the evolution of technology on colliders, on energies that we can access, I think the estimative was that we would be able to construct such accelerator in, I don't know, I think it was 300 years from now, right? 1,350. Yeah. So around 300 years from now. So we are very far away from that. And that's why we believe that direct observations of quantum gravity are still a long way ahead. Well, leaving aside this difficulty or this challenge to probe quantum gravity directly, let's try to see what happens on the theoretical side. Let's try to see how we can quantize gravity. And one thing that we can try to do is to copy what we do with other fields in nature. We know how to deal with quantum field theory from a canonical formalism, also from a path integral formalism. And we can try to apply this formalism, these two different formalisms, to gravity. If you follow the canonical formalism, then essentially what you need to do is to deal with commutation relations between the metric and the corresponding conjugated momentum. And this is challenging because you have very non-trivial Hamiltonian constraints, and they also lead to the problem of time. And one of the issues with this version, or one of the challenges of this version, is that you are generically breaking manifest covariance in this way. I'm not saying it's impossible, it's just a bit difficult to do. This part is also difficult, but I prefer this one, so I would say that this one is more difficult, at least for me. Yeah. Yeah, it's because you have to define a time-like surface, right? To impose, we are imposing equal time commutation relations. Yeah. Well, my favorite way is the path integral formalism. And what we would like to do here is to integrate over all possible geometries, so integrate over all possible metrics. This is also challenging. What we can do in practice, at least at some level, is to integrate over metric fluctuations, and that's what people usually call the graviton. If you quantize this metric fluctuation, you have what people call the graviton. But this is also not perfect. There's also, we have to deal with the problem of ill-defined path integrals. We also break some form of invariance, in this case here, manifest background invariance. Well, but let's try to go ahead and see what we can do about this problem. People actually try to do that. And if you just apply standard QFT methods, so for example, in the 60s, Feynman and de Wit, they used this idea of covariant formulation based on fluctuations around a particular background in order to compute three-level amplitudes in a QFT style, and they are able to recover some of the classical results from there. So for example, you can recover the Newtonian potential from amplitudes. I don't know if they did this at that time, but you can also recover, for example, light bending from QFT amplitudes, three-level amplitudes, in this way. But the problem at that point was that there was some apparent violations of unitarity. Later, Tufte and Veltman, they tried to go beyond three-level amplitudes, and they did the first computation of one-loop divergences in quantum gravity, and they found cancellation of one-loop divergences. And I need to tell that at this point was already expected that gravity would be a non-renormalizable theory. But they found this cancellation of offshore divergences, so there was some hope at that point that there is some miracle cancellation of divergences and things are actually fine, at least on shell. But that's not true. So during the 80s, Goroff and Sagniotti did a very complicated calculation, and look at two-loop divergences in quantum gravity. And they found that there are terms that are divergent but do not vanish on shell. So the conclusion here is that quantum gravity is indeed non-renormalizable. If you try to apply standard QFT methods for gravity, you get a non-renormalizable theory, which at the end of the day essentially means that the theory is not predictive at a fundamental level. Okay? Well, this means that we need to change something if we want to quantize gravity. One way is to give up on UV completion. So let's say you don't care about extending the theory to arbitrarily high energies. Let's try to extend this to up to a given energy that defines a cutoff in the theory. And that's the effective field theory formalism. So the idea here is that you can write an expansion for the dynamics in powers in some way respecting some rule of power counting. And within this effective field theory paradigm, if you have energy scales, if you are looking at processes that are characterized by energy scales smaller than the Planck mass, then these extra terms beyond the so this is essentially the general relativity part of the expansion. And then you have a bunch of other things with unknown coefficients that can be, essentially parameterize deviations from general relativity. These extra contributions here, they are suppressed by powers of energy scale divided by the Planck mass. And this is actually true to all orders in a loop expansion. This is actually a very good way of computing quantum corrections, because this suppression here is of order 10 to the minus 17 because of the relation between electric scale and Planck mass. So of course, now I'm just using C equal 1, so light velocity equal 1, so mass is equal energy in this context. So this is a very tiny number. So this actually defines, as long as you stay in this regime, this actually defines a very good perturbation theory. Actually better than any other perturbation theory that we have around, describing fundamental interactions. So for example, if you are around the electric scale. And you can use this, for example, to compute quantum corrections to the Newtonian potential. So this is actually the quantum correction. This is a post-Newtonian correction. This comes from loop expansion, but this is actually a classical effect, a post-Newtonian classical effect. But this was the first, so this gives the first quantum correction in this, let's say, effective field theory framework of quantum gravity. And well, I think it's fair to say that this is basically the only solid result that exists in quantum gravity, or one of the only solid results that exist in quantum gravity. And, sorry? No, the number has been disputed and so on, but, well, assuming that people now understand the number, yeah, that's a good point. It took a while until people get the right number. I think I have the right number here. But yeah, so, but my point here was, this is a result that any UV complete theory of quantum gravity should recover in some way at intermediary scales. So the conclusion here is that we do have a quantum theory, a theory of quantum gravity. The problem is that it's not UV complete. And we are ambitious. We want more than that. We want to describe nature and its most fundamental aspects. The second term is it's a post-Newtonian term. I think you can get this from GR directly. Sorry? Why? I don't know if there is a conceptual reason for that, or if it just come out from the calculation. Yeah, I don't know if there is some reason for that. Yeah. Well, then one important thing here is that this is very small compared to this in scales where we can measure something. Well, so if we want to describe quantum gravity in a fundamental way, we need to change some paradigm. So this means that we need to, come on, every time that I have some fun image, this means that we need to think. So we need to change something. That's what we understand. So either we can start from different classical dynamics, or we can use some new symmetry principle. We can try to quantize different degrees of freedom. We can try to use space-time discreteness in our favor. I mean, to postulate that space-time is discrete and use this in our favor. We can try to use non-perturbative methods instead of standard perturbative QFT, for example. Well, there are two candidates for this that are very popular. String theory and loop quantum gravity. And just now I realized that it's fun that string theories also comes with these loops. But yeah, this is loop quantum gravity. Well, these are the very popular kids. So if you go to the internet and if you search for quantum gravity, these are the first ones that you're going to find. In string theories, particles are actually composed by something else. So they are composed by vibrating modes of fundamental strings. Because of this non-local character of strings, basically you don't have any more point-like interactions. This is the way that they deal with ultraviolet divergences. And one of the nice things about string theory is that this is a unification theory. So the idea is that the graviton, so the particle that mediates gravity, arises as a string excitation, but also other particles arises as strings excitations. So that's a heavy candidate for unification theory, unified theory. The problem is that there are several undetected stuff. So string theories, at least the modern versions of string theories, are based on supersymmetries, and this was never detected. This also requires extra dimensions for self-consistency, and this was also never detected. It's also unclear whether you can recover the standard model of particle physics from string theory. Loop quantum gravity was born from canonical quantization. So people try to use different dynamical variables to deal with the constraints on canonical quantization of gravity. And they did this in a way that you can introduce volume and area operators in the same way that we introduce position operator in quantum mechanics. Here you have volume operator and area operator. And one of the things that follows from this quantization is that you have discrete spectra for these quantities. So you have some notion of discrete space-time in this way. This has been applied to cosmology and black holes, but it also has some downsides. It's unclear how to recover the continuum limit. It's unclear if we can add standard model to this picture, and so on. So at the moment, we don't have any, I mean, the two main candidates, the two popular kids in school, they still have some issues that we need to understand. There are actually other kids in school. We hear more about the first two ones, but there are many alternatives to quantum gravity. Nowadays, there are also people trying to connect these alternatives. If you want to learn more about this approach, for example, you can look at this book edited by Daniele Orici on approach to quantum gravity. This already has, I don't know, is around 15 years old, I think. And there is a more recent handbook of quantum gravity that explore, well, I think it basically explore all the approach that have been, well, at least that has more than one people trying to do. It's not a handbook. I mean, it's the usual thing that we call handbook in science, right? As I said before, there are some people trying to unify this approach, so to gather the kids. And this is the International Society for Quantum Gravity. Antonio in there is one of the founders. Satish over there is also very active on this. And they are trying to put together the different communities of quantum gravity. And I mean, the idea is that we should talk to each other and try to solve common problems. Well, now I'm going to move to the part that I'm very suspicious to talk about because, well, this is my favorite way of addressing the problem, which is the renormalization group approach to quantum gravity. In particular, what we call asymptotic safety. The idea of asymptotic safety, or the main idea of asymptotic safety, is that we go beyond perturbation theory. And we try to get rid of the lack of predictivity of non-renormalizable theories. How do we do that? We assume that high-order terms that are generated in a non-renormalizable theory is actually part of our theory. And we conjecture that there is a new symmetry principle that is realized in gravity, which should be responsible to restore predictivity of the theory, despite of being perturbatively non-renormalizable. And this principle is scale symmetry, or sorry, quantum scale symmetry. Scale symmetry is this kind of self-similar behavior that we obtain by zooming or zooming out something. And the notion of quantum scale symmetry is that this is not a symmetry of the classical world, but only of the quantum world. So you starting from a classical space-time, things are not scale invariant, you zoom in, you see different structures, and at some point you start to zoom in even more, and then you get to the quantum regime, and you have this emergent self-similar behavior popping up. Yep. There are some associations between quantum scale symmetry and minimal length, but they don't have a fundamental. So there is a difference between what we call classical scale symmetry and quantum scale symmetry. Quantum scale symmetry has to do with the behavior of dimensionless couplings. Yeah, but it's indeed, it's hard to conciliate minimal length with this. But I just want to mention that there are some works doing that, where they explore this, but I don't remember the details. Okay, so that's not the common view, at least. Okay. Well, the idea is that, so I mentioned that this is a renormalization group approach. And the idea is that this is a renormalization group approach because what we call quantum scale symmetry is related to fixed points of the renormalization group flow. We do have fixed points in other interactions. So for example, if you look at the strong interaction of the standard model, you have this kind of asymptotically free behavior for the strong coupling, for the QCD gauge coupling. This basically means that the couplings, they go to I mean, if you increase the energy scale, then you reach a fixed point at vanishing coupling. And then once you get there, you stays there. And the idea of asymptotic safety is to generalize this picture. Actually, you'd want to do this in a version with several couplings, namely infinitely many couplings. But just for simplicity here, just have one coupling. And instead of going to a vanishing coupling, you stays at a constant value for dimensionless couplings. And the fixed point regime essentially corresponds to the scale invariant regime of the theory. So here we can see that in this region here for small values of energy, things are varying. So we are not in a scale invariant regime here, but then we tend to a constant value, and then we enter a scale invariant regime. Okay? Well, one of my favorite pictures in asymptotic safety is this one. I have been using this since my PhD thesis and recycling this. And this is the notion of what we call critical surface. You can define a space with all possible couplings associated to operators compatible with the symmetries of the theory. Here, there is a conjectured fixed point. And the idea is that this critical surface correspond to all points that emanate from the ultraviolet fixed point. And the idea is that since asymptotically safe trajectories are restricted to this finite dimensional critical surface, if it is a finite dimensional critical surface, then we only have a finite number of free parameters in the theory, and that's the way that we recover predictivity. But having said that, this is a conjecture. So quantum scale, I mean, the idea is that we conjecture that quantum scale symmetry or this fixed point is realized in gravity. If you want to learn more about this, you can check these books, the first one by Roberto Percacci and the second one by Martin Reuter and Frank Sarasek. You can also see some online lectures at the GraphBR channel. There are some functional renormalization group lectures by Antonio, who is over there. And this is a kind of prerequisite to the way that we do asymptotic safety. And there are some asymptotic safety lectures that I gave together with Anderson Thomas. Well, these are quite old lectures. I guess that both me and Antonio, we changed a bit our view of the field after all these years. But, well, I think it's still a good point to start. This is for Portuguese speakers only, sorry. For non-Portuguese speakers, you can also check the ISQG channel, and there are some lectures by Astrid Eichhorn on asymptotic safety in there. Well, the question that the million-dollar question here is whether quantum scale symmetry is indeed realized in gravity. And we have several indications, but not a proof, coming from functional renormalization group methods, which is based on this ugly equation here. This equation here is ugly because we don't have much control of systematic errors. There are also issues related to Euclidean versus Lorentzian signature, and there are other issues that I'm not going to comment on this colloquium. There are also other indications coming from different methods. For example, people try to use what we call dynamical triangulation, which is basically a discretization of geometry combined with lattice simulation, combined with Monte Carlo simulations. And the indication from for asymptotic safety coming from this kind of methods is this kind of phase transition line here, which presumably correspond to a second order phase transition line. And the idea is that you would be able to recover the continuum limit, in other language, reach a fixed point from this kind of phase transition. There are also other ideas that have been explored. So for example, exploring asymptotic safety from tensor models. Antonio is in there, and you can ask him questions about this, not to me. But the thing that I just want to comment before closing my seminar is about the possibility to connect quantum gravity with experiments from this kind of approach. As I said before, we expect that quantum gravity is really relevant around here. And this is where we can perform experiments. And there is a huge gap between these two scales. So what is the future in this direction? And the nice thing about renormalization group approach to quantum gravity is that the renormalization group flow allows us to connect different scales. There was very exciting results about this in the past 15 years. For example, there was a prediction of the Higgs mass from asymptotic safety with a lot of approximations on top of that, to be fair, but it was a nice result at the point because it was 3 years before the actual discovery or the actual detection of the Higgs boson, and they got the right value. There are ideas of solving the hypercharge triviality problem. So that breakdown that I mentioned in the standard model, in principle, there are ideas on how to solve this from asymptotic safety. And there is even the idea of performing a UV completion of standard model from this kind of scenario. And the most recent work in this direction, that was not a funny plot, but yeah. The most recent work in this direction, or the most complete work in this direction, was by, well, we cannot see the reference here, but by the group of Jan Pavlovic. And what they did was to, I mean, they managed to connect all standard model couplings. Here there are just a few of them, but they managed to connect all standard model couplings with a free fixed point because of the inclusion of quantum gravitational effects. And well, the idea here is that how we can use this to say something about gravity. So the idea here is that because asymptotic safety works as a kind of boundary condition in the UV, we can make predictions or impose upper bounds on couplings in the infrared, or impose bounds on couplings on the infrared. And this can be compared with experiments. So that would be the idea of connecting experiments or phenomenology with quantum gravity from a renormalization group approach. Well, just before I close my talk, let me talk about ode ultraviolet. 5 minutes? Okay, yeah, it's okay. Let me talk about an ode ultraviolet complete theory of quantum gravity. And well, I'm currently quite excited about this. So it's not very popular, but I'm going to talk about this, which is general relativity plus higher derivative terms. So the idea is that if you enlarge general relativity with higher derivative terms, then you change the behavior of the graviton propagator, and then you get a renormalizable theory to all orders in perturbation theory. So you can do, in principle, you can do perturbation theory with that. More than that, the theory is UV complete because there is a region in the parameter space where the couplings are asymptotically free. So why we are not celebrating? It's because this theory has ghosts. And for this reason, this kind of theory was, well, not seriously considered for several decades. But now there is a new perspective. Maybe these ghosts are not as scary as this one, but could be like Casper, a friendly ghost. So some perspectives on this are that, in principle, this possible particle that we call ghost, this is actually a fake particle. This is the idea of fakions. There is also the idea of Merlin modes, that these ghost particles are actually moving backwards. And for this reason, this would not cause any problem with unitarity. And my favorite one is that, well, I should actually have some quotation marks here, but that the idea is that in principle, we have some conjectures that ghosts could be confined and would not appear as asymptotic states in the theory. So that would not cause problem with unitarity. Well, with this, let me go to my final remarks. In this talk, I try to explain why we believe that we need to quantize gravity. And the idea is that we came a long way on understanding the fundamental building blocks of our universe with standard model and general relativity. But both theories, they break down at very small distance or high energies. And one possible point of view, and that's the point of view that motivates me to study quantum gravity, is that quantum gravitational fluctuations may be the missing ingredient on that. The question whether we have a theory of quantum gravity is yes, we do. We have the effective field theory paradigm. It's just, I mean, not UV complete. So we can do consistent calculations below the Planck scale. UV completion requires some change of paradigm. And there are many approaches to this problem. I try to mention a few of them here. It's still unclear if one of them, which one of them, or if any, is actually correct. And in general, we still have a a long way to go. So we are not there yet. With this, I would like to thank you for your attention.
Question?
Two quick questions. Go back 2 slides, please. One more. Counting.
This one?
I was just curious to what exactly is this theory that you were talking about? Is it like Starobinsky? What are the higher derivatives? I consider a general scenario.
It's general relativity plus curvature scalar square plus Ricci square. So R min U square plus R square.
Okay.
Just R square, which is the Starobinsky model, does not make it renormalizable.
Okay, fair enough. And regarding the effective Newtonian potential that you showed with a quantum correction, I was just curious to know up to what energy scale that correction would be valid. Because surely it wouldn't work for Planck scale, but if not, up until what energy does that hold?
The upper bound is the Planck scale. The idea is that as you get close to the Planck scale, this approximation starts to get worse. But the upper bound is the Planck scale because you need suppression by these ratios here, which essentially means that this ratio has to be smaller than 1.
Okay.
So I mean, the idea that effective field theory is not UV complete is because you cannot go beyond Planck scale.
Thank you.
More questions?
If there are no questions, I have a quick comment regarding the bending of light. That was not done by Feynman or DeWitt. It was done only in 2006 by Beram Bohr in Copenhagen.
I think there is even earlier results.
Really?
At 3 level, there are even earlier results.
Okay.
I think
using scattering amplitudes, they did it in 2000.
Yeah, but this is the with loop corrections, right? I think 3 level, there are even earlier results.
Earlier? Okay.
At least I'm almost sure that Ascioli, for example, has some works from the 90s.
Okay,
and I don't think he was the first one.
Okay, we will check then. And I see a typo there. In particle physics scale, you showed the Planck scale and particle physics. You have 10 to the 2 GeV. Make it 10 to the 4 GeV.
Where?
The fourth from the last. Yes,
This one?
That's 10 to the 4 GeV. So we are good until 10 TeV now.
Well, here I was referring to electroweak scale, not the.
Sure.
Yeah.
So then it's electroweak scale, yes.
Yeah, but electroweak. Yeah. Okay.
Questions?
Okay, so maybe just to understand this asymptotic safety. So you say that you postulate this, I mean, scale invariant fixed point, and this comes from a phase transition?
The idea from a lattice perspective is that this would correspond to a second order phase transition.
So do we have any idea what this phase transition is? And then just to understand, like this phase transition would be as you lower the energy, you go through this phase transition, then you have like your critical surface, and which only has a finite number of coupling constants, and that's why you can somehow have your theory for quantum gravity. But then maybe it doesn't make sense, my question. But then if you go to energies higher above, like then you're still again somehow subject to energies which are below the phase transition, right?
So the idea is from this UV complete theory, in the deep UV, you are at the fixed point. And then you stay at the critical surface when you flow towards the infrared.
I just don't get this picture. Like usually you would say you have a phase transition and there's like energy range below and above, but you somehow say there's nothing above the phase transition. Like it's not that.
So, yeah, I mean, the idea is to realize this as a fundamental theory. So you get there and you stay there.
You get there and you stay there, but you could. But then it's not really like a phase transition. It's like
So-
like you say that in the UV you're going to a critical point, but this is like manifestly critical, and you stop there, or maybe it's just like confusion in my head, because normally like a phase transition is you have a critical temperature, and you have temperatures above, you have a certain phase there, and then you go through your critical point and you go to some, right?
I don't think this picture would exactly apply here as a fundamental theory.
So
I think Antonio has some comment about
So it wouldn't be really a phase transition. It's just you go to a point that has a scaling variance and you're stuck there in the critical point.
When I mentioned the phase transition is because from the lattice perspective, this is identified as a second order phase transition.
But then you would have some energies above the critical point and energies below the critical point, right? In this picture, or is it doesn't this make? Maybe I'm thinking.
No,
Yeah, I think Antonio has a better
think-
understanding about that.
If you think of the lattice as really being a physical thing
Yeah.
and not just a device to regularize the theory, then your perspective is correct.
And then again, like the scale above, you don't have any idea. So in
Yeah.
this picture, you would
But-
just make a progress up to a certain scale, but beyond this, you're lost again.
Yeah, but for those that's doing CD causal dynamical triangulations and so on, they take the discreteness or the lattice just as a regularization device.
I see.
There are those approaches like loop quantum gravity that you have a minimal length or a minimal area. And for those, discreteness is fundamental. So there is really a physicality in this regime that you're referring to.
Okay, thanks.
You're not convinced.
Just any more questions? Just for the students that are not getting, Tobias works in condensed matter theory, and he works with renormalization group flow in another context. So he's trying to understand how these kind of methods that are very similar to his own are applying in this context, right? For the students to understand. There was another question.
So I suggest the title to you, and then
Yeah.
there was a unification of microcosm and macrocosm.
Yes, yes.
But yet, even if you get unified theory, quantum gravity, and all these things, there's still something that maybe you cannot unify the microcosm with macrocosm, because this implies some type of reductionism. What I have in mind, for instance, if nuclear physics, okay? So we have Kitsuji, quantum chromodynamics, which explains the really fundamental aspects of nuclear interactions. But when you go, for instance, construct an atomic bomb, a nuclear bomb, nothing of that is relevant. You have a different framework, different concepts, different quantities.
Yeah.
And it's really, people don't know how to relate quantum chromodynamics to the old nuclear physics, because people construct the bomb before knowing about quantum. What do you think about this? So the question is, even if you have a quantum gravity theory, perhaps it's not yet the unification of microcosm and macrocosm.
Well, I mean, in this sense, the idea is you try to find from this perspective of unifying things in terms of quantum gravity is to try to find what are the building blocks. So the fundamental.
This is small, but this is small.
It's really small, but it does not mean that it's useful to do macro physics, right? Because as you said, in order to do nuclear physics, you have effective models that works better than trying to use.
But the thing is that we even don't know how to relate.
And we don't know how to relate them. Yes, yes, that's true. That's true. So, I mean, what we know so far is that we do have different regimes where there are the convenient degrees of freedom to describe things. And what are the convenient ingredients to describe things. We're not going to use quantum gravity to describe the free fall of this bottle, if I, but
so perhaps you need
Yeah.
a completely different concept of gravitation in order to do that. That's what.
yeah.
Now we have a contribution from Felipe.
Hi. Very nice presentation, Gustavo. I have a quick question. In the asymptotic safety paradigm, you said the existence of the fixed point is a very important concept. So you said that there are evidences about it. Can you comment about it? Some evidence?
Well, as I said, there are some indications from lattice, and that I don't know much about that. Most of the evidences come from functional renormalization group calculations, and they are based on this kind of approximations where you truncate the dynamics and solve the flow equation under this truncation. And what we see so far is at least a kind of numerical convergence on some of the properties of fixed points if you increase the size of the truncation. But I mean, that's not a proof of the existence of the fixed point. It's a fair question whether adding things that are not in the original truncation, if this spoils everything that you have. It's unclear if this happens. There are a bunch of other technical issues like scheme dependencies and so on that are not under control. But yeah, I mean, from the original calculation from Reuter in the 90s to now, I think it's fair to say that at least we are more convinced that there is something. But now we need to convince others that there's something.
Thank you very much.
Okay. Sorry, Nilsson. Okay, I have a response to what you said. So in quantum gravity, what we are trying to do is reductionism, right? But the other way is emergence. So Phil Anderson famously told, more is different, right? So just because we know QCD, we cannot make up nuclear physics. So again, Ken Wilson taught us this effective field theories, right? So we have this as input, but we can never start with with quantum gravity and then predict the weather. So it's never going to happen, even with a good theory of quantum gravity, with good theory of gravitation. So we have to live with that fact. We can go down reductionism, and there is emergence. So one cannot substitute the other. So macrocosm is going to be there. We cannot explain a whole of macrocosm with the microcosm. Never.
Sorry, I mean, I just think that, we also just say, well, integrate the modes, just integrate from the QCD scale to nuclear physics, and you are going to get what you want. But of course, I mean, in practice, we know that this is just impossible. So I agree with you that it's impossible, but I just think that we also will say, well, integrate it. And you're going to have the effective field theory for nuclear physics from QCD. Yeah.
From the YouTube channel, but
Could be worse.
Pergunta? The question, CBPF into the 21st century. But the question was about the recent work in quantum consciousness. So that's why I said. So nós.
I think.
Pergunta. The idea of a quantum theory of gravity would strengthen the implications of the recently nominated electromagnetism plus quantum field in humans. I would guess he's talking about the Hameroff thing of quantum consciousness. That has nothing to do with quantum gravity. But thank you, Ricardo de Andrade. We tried. More questions? So just to finish, Gustavo, if you could, the last thing that you cited, you said your favorite thing. If I'm not mistaken, at the end of that meeting that we were together, we saw a calculation about confinement of ghosts
Yeah.
in QCD.
Yeah.
So could you give an update on how constant ghost condensates and quantum gravity are going?
I don't have anything new to say about that. I can say that I'm very excited by that result. I think that so
You can talk about
yeah.
that,
So
or-
the result that he's telling us is a paper that came out recently by Manuel Assorey, Gaston Krain, and Ilia Shapiro. And this was presented in a conference in São Paulo a few months ago. And what they did in there was to show that in a theory with high derivative terms, which classically would have ghosts, given certain properties, they could condensate into half particles. And that resonates a lot with this idea of Holdo and Rein. Although, I mean, in what they did in there was related to super renormalizable theories. So I guess that they plan to apply this to super renormalizable theories of quantum gravity. I think this can also be applied to renormalizable theories, but that's just what I guess. And I hope to show this at some point.
Okay, let's thank our speaker. For those of you that are on BSCG, tomorrow, 8:30, we're all back here.
Yeah.